Welcome to Aman Water, where every drop counts. Imagine a glass of muddy water, cloudy, full of suspended particles. How can we make it clear again? Before disinfection, we first need the impurities to settle. Welcome to the fascinating world of sedimentation. Sedimentation is a physical separation process. It's based on a simple principle: letting gravity do its job, pulling heavy particles down to the bottom of a tank. In water treatment, this step comes before filtration.
It reduces the amount of suspended matter, called TSS, total suspended solids, making the next stages easier and more efficient.
There are several types of sedimentation, depending on the plant's needs. Simple gravitational sedimentation. The water remains still in a settling basin for a few hours, perfect for heavy particles. Lamellar or inclined plate sedimentation uses slanted plates to increase surface area, compact and common in small plants. Accelerated or dynamic sedimentation uses coagulants or flocculants to speed up particle settling. More efficient but requires fine control.
Personally, I like lamellar sedimentation. It's like a slide for particles.
But some particles are so tiny that they stay suspended. They're too small to fall on their own. That's where chemistry comes in. Coagulants neutralize the charges of fine particles. Flocculants make them gather into larger, heavier clumps, called flocs.
It's like a party where everyone holds hands and ends up at the bottom of the pool.
Now, one question always comes up: how long should the water stay in the tank to be properly clarified? That's where an essential concept appears: retention time. It's the time it takes a drop of water to travel through the whole tank. It depends on two things: the volume of the tank and the flow rate of the water passing through it.
So if I know the flow rate and I want the water to stay for 3 hours, I can calculate the volume one need.
But that's not all. It's not just about total volume. The particles must have enough time to fall to the bottom during that journey. Here comes another key concept: settling velocity. We also call it the terminal velocity, and it can be estimated with Stokes' law, depending on the particle's diameter, density, and the fluid's viscosity. If the settling velocity is too low and the water flows too fast, the particles don't fall, they escape with the water. And that means failure. In short, the higher the flow rate, the larger the tank must be to ensure good retention time. The finer the particles, the slower they settle, so we need more surface area or slower flow.
So, does dirtier water always mean a bigger tank?
Not necessarily. Sometimes engineers use flocculants or lamella settlers to save space while keeping efficiency high. Designing a settling tank is all about balance between flow rate, volume, retention time, and particle settling velocity. That's where engineering truly shines. Designing a tank that's just big enough, efficient, not wasteful, and produces water already well clarified before the next treatment steps. Let's take a concrete example. Imagine a plant that treats 100 cubic meters of water per hour, and we want the water to stay at least 3 hours in the tank.
That means the tank must have 300 cubic meters of useful volume. What does that mean in practice?
If the tank is 2 meters deep, we can calculate the surface area, for example, 15 meters long by 10 meters wide. But there's another thing to check. The horizontal velocity of the water must not exceed the settling velocity of the particles. If particles settle at 0.5 millimeters per second, the flow must be slow enough so they can reach the bottom in time. That's the art of designing a sedimentation tank, adjusting the volume, geometry, and velocity to fit real-world conditions. And now, grab a glass of water and stay hydrated. If you're into this topic, don't forget to subscribe, hit the bell, and come with us to explore the world of water.